This conference will now be recorded.
Very good evening, students. Today we'll solve few numerical problems on fluid mechanics. That means the properties of properties of liquid. Here in this fluid mechanics, we'll come across problems from viscosity, surface tension, and most importantly, the capillary rise. So we have already discussed many questions on surface tension, viscosity related questions. So two or three more we will discuss in this session. Then what we'll learn today, or we'll recap our conceptual understanding on the capillary rise, contact angle, and those kind of things. And thereafter, in the next class, we'll take some questions on capillary rise topic. Okay. So let us solve two or three remaining questions on viscosity and surface tension part. Then we'll go to the recapitulation or revisit of the concept of capillary rise. Okay, so we have got this question. The question says, raindrop with radius 0.3 mm falls from cloud of height 2000 meter above the ground. Assume the drop is spherical through its fall and the force of buoyancy may be neglected. Then the terminal speed attained by the drop. Okay, so here we have to understand one point. When a raindrop falls through different layers of atmosphere, you know, this is fluid. So when it falls through different layers of atmospheres, then it actually feels resistance due to the viscosity as well as buoyant force. But for this case, you have been instructed to neglect the buoyant force. So there will be only two forces. One is mg in the downward direction, and another one is the viscous force fv. Okay, buoyant force is neglected. So by Stokes' law, we know the viscous force is given by 6 pi r into eta, coefficient of viscosity, and v. So this v is actually the terminal velocity. So as this drop falls through the atmosphere, it is actually gaining more and more velocity. Hence the viscous force also will be increasing, because you know viscous force is always proportional to the speed. Okay, and at some point of time the speed will be such that the viscous force and the weight of the drop will be exactly equal. That means the drop will have no net force at that particular situation. So when there is no net force on any object, that will be actually moving with a constant velocity or uniform velocity, or if the object is stationary, that will remain stationary. That is the Newton's first law first law, okay, in the mechanics. So when this situation occurs, then the speed attained by the raindrop is called the terminal velocity. So we'll be making use of the Stokes law and write this. Let us just go to the next page, or maybe let me write it here itself so that I can use the information over here. So the viscous force is obtained by Stokes law, that is 6 pi eta r. R is the radius of the raindrop, and v is the terminal velocity. Let us take that vt is equal to m into g. Okay, so radius here, capital R, radius of the raindrop is given as 0.2 mm. Okay, g we have to take 10 meter per second square. Okay, and the density of the air is given, density of the water is also given. Okay, so how do you get small m here? Since it is spherical, ideally, then I can take 4 by 3 pi r cube. This is volume into rho. Rho here it is given Fw. Okay, so this will be the mass. Okay, so let me just equate these two things. Okay, let me write it here, m into g. That means, you know, here 4 by 3 pi r cube Fw into g. So what is v terminal from here? So Vt will be 2 by 9. Pi cancels out. This r cancel one r here. This will be r square. So I'll write here r square Fw and g divided by eta. Okay. Let us put the values over here. So this 2 by 9, it is fine. Eta is given as, okay, it is this one, 1.8 into 10 to the power minus 5. This r square is 0.2. That means 2 into 10 to the power minus 4 in meter. So this will be, square of that will be 4 into 10 to the power minus 8. Okay. What else? We have this as 10 to the power 3 kg per meter cube, and g is for the 10. Okay. So look, if I just take this 10 to the power 5 minus 5 in the numerator, so what will get? 10 to the power 4. So this will be 10 to the power 9, and ultimately you will get this 10 to the power minus 8 read off. Okay, so you'll get this 10, and one more 0 here just to erase this one. So I'll get this. Okay, so 400 by 81, this is in meter per second. Okay, so if you do the calculations, 400 by 81, see, 400 by 81, so it will go with 4 6. Okay, so here it will be something like 9. Go 1 point will come here, so 9, this is 32, sorry 72, This is 1, this is 4, maybe one more 0, so there will be again 4, okay, coming up. So see, it is coming around this one, okay. So 400 divided by 80 gives you nearly 4.94 meter per second. All right. So this is the terminal velocity of the raindrop. Okay. Now let us go to the next problem. Okay. So this problem, I need to give you the options over here. Let me first give you the option. See, the question says a certain number of spherical drops of liquid of radius smaller coalesce to form a single drop of radius capital R and volume capital V. If T is the surface tension of the liquid, then if T is the, okay, this is there. So if T is the surface tension of the liquid is, then see option A says energy CVT whole into 1 over minus 1 over smaller divided by 1, okay, so minus 1 over capital R. This is, let us, then liquid, then liquid is, that means see, this much energy is released, sorry, it is just released. Option B says energy is neither released nor absorbed, or not absorbed, okay, sorry, neither nor, so neither released nor absorbed, okay. Option third says energy for VT energy for VT whole into this factor 1 over smaller minus 1 over capital R is released. Option D says energy is equal to 3 VT 1 over R plus 1 over capital R is absorbed. Okay, let us first try to understand this question and then we'll solve it. A certain number of spherical drops of liquid of radius small r coalesce to form a single drop of radius capital R and volume capital V. If T is the surface tension, then the liquid will release or increase the energy first of all, and how much energy it will release or increase, or whether there will be no release or no absorb. Okay, so absorption. Okay, let us explain it here. Just let me explain it here. Suppose we have identical, let us say. Okay, so drawing may not be identical. So I have this many, some n number of identical drops of radius smaller. So when they combine, they make a bigger drop, single bigger drop of radius capital R. Okay, so what will happen when many drops combine together to form a single drop? See here, there will be decrease in surface area, decrease in surface area. Okay, when a single drop is broken into many spherical drops, then the surface area increases, and when many smaller drops combine to have a single bigger drop, then there will be decrease in surface area. And we know surface energy is equal to surface tension T into the change in the area, change in surface area. So since here the surface area decreases, so energy also decreases here within this spherical drop. That means the amount of energy, this much energy gets released. Okay, energy is released in this case. Okay, because the surface area available over here will not be able to hold the energy which was earlier with all of them. Okay, so energy will be released. So this much we have understood. What is the amount of energy that is going to be released? That is T into the change in the area. Now it is easy to solve. So what is the area? Say, 4 by 3 pi small r cube n is the number, is equal to 4 by see 4 by 3 pi capital R cube. So this is given, right? So 4 by 3 pi. So n will be r cube by small r cube. This I can get. Okay. So what is the change in the surface area? Let us find out. Or change in the energy or release energy itself, we can write directly. T into change in the area. That is, say, I have earlier we have see 4 pi r square into n, and here it is 4 pi capital R square, right? Look, then this T, let us take this 4 pi out. Okay, this R square, this is n, the value of n I'll put here as this, minus 4 pi R square, Okay, this is the thing. Now look, this 4 pi t excuse me, 4 pi t r cube, let us take common, and this is c 1 by r minus 1 by capital R. Okay, now here we know v is equal to 4 by 3 pi r cube. Then what will be 4 pi r cube? So 4 pi r cube will be is equal to 3v. Okay, from here. So this value 4 pi r cube, I'll put it here as 3v, and this t was there, so it is whole into 1 by small r divided by, sorry, minus 1 by capital R. Okay, so you can see the amount of energy which is getting released is this much, 3vt whole into 1 by r minus 1 by capital R. So here, see, there are options over here. 3vt, this one, this much energy will be released. So option A will be the correct answer for this question. So students, as I mentioned, I'll be solving two questions related to surface tension, viscosity, etc. And thereafter we'll revisit the conceptual understandings of capillary rise. So let us learn that part of fluid mechanics. Okay, so capillary rise or capillarity, whatever you say. So before we understand what is capillary or capillary rise and why the capillary rise happens, those things, the main responsible factors for this capillary rise are two forces and interplay of those forces. So what are those forces? Those are cohesive force and adhesive force. So adhesive force and cohesive force are the main reason why there is a capillary rise, or there is a curvature at the point of contact between the liquid and a solid surface. As I go along, I'll be discussing about that a little more. So actually there is a tendency when a liquid surface usually comes in contact with a solid surface, at the point of contact the liquid surface become curved. So that nature of the curvature depends on the cohesive forces, or the reason for that curvature at the point of contact between liquid and solid surface are the adhesive and cohesive forces. So what are cohesive forces? Cohesive force is the force of attraction between the molecules of same substance. Okay, same substance. Like if I have liquid drops like this, okay, or liquid molecules, so they have attraction between them. Okay, so this is actually cohesive force. If I have a solid substance, so there are molecules inside them. Okay, so these solid molecules, okay, if they are like attraction between the molecule is called cohesive forces. That means the forces between same molecules of the same surface, same substance, is actually cohesive force. If you ask me to give some example, I can give you. See, because of this cohesive force, you know, when two drops of liquid, you take two drops of water and then bring them very close to each other such that they touch each other. So as soon as they touch, they will actually combine to a single one. Okay, this is due to the cohesive force. They coalesce to form a single one. So this is due to cohesive force. Further, if you take a mercury, okay, mercury drop and try to break into different number of drops or multiple number of drops, it is very difficult because the cohesive force of mercury is the largest among the liquids. Okay, for mercury the cohesive force is much greater than that of the liquid. Okay, sorry, water. So water has less cohesive force than the mercury. And see, we have seen the examples of cohesive forces. Now I'll tell you one good information, that is the cohesive force for like among the solid molecules is much greater than the liquid, and the cohesive force between the molecules of liquid is further greater than the gas molecules. Why is it so? The cohesive forces among the solid molecules, or in the solid, cohesive forces in the solid is the strongest one, because they have, see, solid has a definite shape and size, definite shape and size. So this is the reason the cohesive force between the solid molecules will be the strongest. Then liquid, they have a definite volume obviously, but they don't have definite shape, no definite shape. Okay, definite shape. So that's why liquid has comparatively less cohesive force, but gas does not have both no shape, no size, or no fixed volume. Okay, so that's why gas has the least, gas molecules have the least cohesive force. Okay, according to the strength. All right, now we'll learn about adhesive force. I hope you are familiar with the adhesive word, because we use the adhesive, the glue or the gum, for sticking to surfaces in case of like covering or closing an envelope, or making some model for learning purpose. There you use Fevicol or any glue gum. So those are actually adhesive. So what, on what principle they work? They work due to the, see, they can help us to stick to surfaces because of the adhesive force. So what is the adhesive force? Adhesive force is the force of attraction between the molecules of different substances. Suppose I have a peach board, or I have a passport size photo I have to attach to the admit card. Okay, during the exam sometime we have to do that. Okay, in JEE Mains, etc., you have to paste one passport size photograph, right? What you do, you take a Fevicol or any glue and then stick to the page, right? Stick to the page like this, isn't it? So this page and the photo page, these are two different surfaces and different materials, and the molecules also will be different. So the attraction between different molecules or molecules of different substances, this force is actually an adhesive force, and for some liquids or some substances, this adhesive force will be very strong compared to the cohesive forces. Okay, cohesive, see the glue itself, they have molecules and they have forces. This force is actually cohesive force. See the surfaces, they have their own molecules and the force between their own molecules is cohesive force. But when we apply the glue, there is a force. So this is suppose glue or gum, and this is the molecules of the page or the photo. So this is different molecule. I can take maybe of different shape. Let me just for demonstration, let me take. So this is some molecules. Okay, so these two are different molecules, and the attraction between them is called adhesive force. So the force of attraction between the molecules of different substances is called the adhesive force. See, for example, Fevicol, I have already told you, while writing in the blackboard, while writing on the blackboard, we are able to write because of adhesive force only. Okay, because of adhesive force we can write in the blackboard. See, the chalk has different molecules than the molecules of the blackboard, and because of strong adhesive force, the molecules of the chalk stick to the blackboard. Okay, or even in pages also what we are writing, so there will be adhesive forces. Sometime, sometime there could be two plates sticking to each other so tightly that we cannot take them or we cannot separate them. Okay, sometimes this happens. So this is because there is some liquid or water in between the plates, and see the water molecules and the plate, they have different molecules, so there will be a strong adhesive force between them. Okay, so because of that, sometimes it is difficult to separate the plates from each other. Okay, so these are the kind of examples or real life examples we have seen, okay, for the adhesive forces and coercive forces. All right, now we'll see the nature of the curved surface. As I said, the liquid surface usually usually liquid surface is usually carved when it comes into contact with a solid surface. Solid surface. Okay, so there is this tendency, and the nature of the curved surface could be, say, if I, let me see whether I have figure. No, I don't have figure here. Let me give you the figure over here maybe. Okay, so suppose I have liquid over here, Suppose this is water over here, and I dip a glass rod. Okay, glass rod like this. You know, this surface, what will happen near this? It will be somewhat like this. Okay, depressed. Compared to this side will be like this. Okay, like this. I'm sorry, let me just change the figure for better understanding. Let me just redraw this. I can give you better figure. If you just take a glass beaker and just take some water in that, you know, you will see that water meniscus looks like this. Okay, and we'll generally take the reading from here, lower meniscus. Okay, that is what we have been taught in the chemistry laboratory, right? So you'll see, if this is water and this beaker is made of glass, we'll see that there is a bending at this particular contact. Okay, so this is the curved surface. Look that. Okay, so this is the water inside, water glass. So water glass. Now if you take in a glass container some mercury, at the point of contact, how it looks, it looks like this. Okay, it will be like this. So look this point. So this is actually depressed over here, this is actually risen here. Okay, this rise here and this gets depressed. This is mercury, the liquid is mercury, and the container is glass. Okay, so this is the thing happens usually when you take any liquid in a container. Basically, with glass it is very much prominent to see. Okay, that's why most of the classes will just take the example of glass water, glass mercury, etc. Glass with alcohol, glass with some other liquid as well. Sometime we'll take the silver content with the water, pure water. Okay, so that thing also we'll see. So this nature, when this liquid will rise at the point of contact and when the liquid will get depressed. Okay, so this is depressed, actually depressed, and this arose or rise, we see rise of the liquid. Okay, and depression of the liquid over here. So at what condition or what situation this rise happens or depression happens? Okay, what are the reason or how adhesive and cohesive forces interplay happens here? Okay, let us see that situations. Okay, let me find here. So when the adhesive force is greater than the cohesive force, then you know liquid will, say at this situation, liquid will wet, the container. Okay, and the meniscus is concave. You look, this is concave. See, in case of water, cohesive force is lesser than less stronger than the adhesive forces between water glass, okay, water molecules and glass molecules. So that's why the adhesive force is more here in case of water glass contact, and at that point of contact the liquid is actually making the container, glass container, wet, and the meniscus will be actually concave, okay, liquid surface will be concave. Now when the cohesive force, or sorry, I think I have written the same here, it will be like this, okay. When the adhesive force is less than the cohesive force, liquid does not wet the container, and the surface will be, upper surface will be convex, the top surface will be, or this is called actually top surface, that is called actually meniscus, will be concave, sorry, convex. See, concave means this and convex means this, okay. So in case of mercury, the cohesive force is much stronger than the adhesive force between the mercury and glass molecules, okay. That's why there will be depression at the point of contact in case of mercury, and the meniscus will look like a convex surface, okay, and it will not wet the glass surface. This is why you use in the barometer, right? Torricelli's barometer, mercury is being used. This is of because of this cohesive force among the mercury molecules, which is actually much stronger than the adhesive force, okay. All right, then see, when the cohesive force and adhesive forces are equal, then the top surface of the liquid will be plane. Liquid will be plane, okay. So it will be like this, and this happens, I'll just give you examples in the next slide when it happens, okay. So this is the liquid surface, so this is plane surface. This happens when the adhesive force and cohesive forces are of same strength, okay, for some liquid. See, now I'll discuss about angle of contact. We have seen that there is a contact point between the solid and liquid. If you see, this is the liquid and this is the solid, the container, this is solid, right, and this is the point of contact, okay, this is point of contact. So at this point of contact there will be either rise or depression, okay, rise or depression of the liquid surface, and depending on that the meniscus will be either concave or convex or plane surface. See, now what is angle of contact? This is another parameter to decide or determine whether the meniscus will be concave or convex or plane surface. But what is this angle of contact? How to take that angle, or angle between which surfaces, or what? Okay, so let us just understand what is angle of contact. It is defined as the angle between the tangent to the liquid surface at the point of contact, and that tangent is actually taken into the liquid. Okay, or sorry, it is defined as the angle between the tangent of liquid surface at the point of contact and the solid surface inside the liquid. So solid surface we have to take inside the liquid. Let me just take this particular point here. Okay, this point is the point of contact here. See, at this point of contact, what is the tangent? If we draw a tangent to this particular water surface, liquid surface, so then this is actually the tangent. Okay, tangent to the liquid surface at the point of contact. So in this case, when liquid is actually depressed or concave meniscus, you look this is actually tangent to the liquid. Okay, tangent to the liquid at the point of contact. This is point of the contact. Okay, here suppose this is P point, this is P point, and I have to take the solid surface inside the liquid. So this is the solid surface inside the liquid. So look, this angle is actually called angle of contact. This is the tangent to the liquid surface at the point of contact, and this is the solid surface, solid inside the liquid. Okay, so this solid surface and this angle of this tangent to the liquid surface at the point of contact, these two are making an angle theta. This angle theta is actually the angle of contact. Okay, further I'll tell once again. So it is defined as the angle between the tangent to the liquid at the liquid surface at the point of contact and the solid surface inside the liquid. Okay, I think this is the best definition you can have about the angle of contact. Don't get confused with other definitions. Okay, this is very nice to understand here from the figure. Now look, this angle of contact can be acute angle, that means less than 90 degree. It can be equal to 90 degree, or it can be greater than 90 degree. Okay, depending on that value of the angle of contact, we can have different type of meniscus or the top surface of the liquid. But this angle of contact actually depends on different factors. Okay, let me write here. Angle of contact depends on how many factors? First is the nature of the solid and liquid in contact. Nature of solid and liquid in contact. In contact. Then second point is the purity or the cleanliness of the surface in contact. Okay, purity, I can say purity of the surfaces in contact. Okay, what more? It depends on temperature of the liquid slightly. Temperature of the liquid. Okay, and also the medium above the liquid surface or above the free surface of the liquid. the medium present above the free surface of liquid. Okay, liquid. So these are the factors on which the angle of contact depends on. Okay, now according to these factors, the value of the angle of contact will be different. See, in some cases the angle of contact will be less than 90 degree. This is called acute angle. In case of acute angle, what happens? In case of acute angle, this liquid, let me just give the points over here. Acute angle you can understand, less than 90 degree. See, point is liquid towards the surface, okay, towards the solid surface of the solid. And second point is meniscus will be concave. Will be concave, as we see in case of glass and water. So in case of glass and water, if this is water and this solid surface is glass, then this theta is nearly 8 degree, nearly 8 degree. Okay, nearly 8 degree for glass and water. So the angle of contact is acute angle. So water actually was the glass surface and the meniscus is a concave one. Let me tell you about this. So this is actually in case of mercury, this happens. Okay, when the angle of contact is obtuse angle or greater than 90 degree. Actually, this there was a question in the NEET paper in the previous year's question. We had solved that when the liquid will at the surface, like when the angle of contact will be acute or obtuse or something else. Okay, so that kind of question may come here from here. So this will not, okay, so does not wet the solid surface. In this case, actually the cohesive force is much greater than the adhesive force. That is another reason. And second thing is that the shape of the meniscus will be convex one. Okay, meniscus will be convex one. Convex one. Okay. Okay, let us go to the middle one. When the angle is exactly 90 degree, look this one. This is the tangent. Since it is plane surface, so tangent will be along this way only, and this is the liquid, solid surface inside the liquid. So this angle is 90 degree, then it is plane surface. What is the example? Pure water. If this is silver, this solid is silver, and the liquid is pure water, then we see this kind of thing. Okay, this curvature we see plane. Okay, there will be no depression or no rise of the liquid at the point of contact. Okay, so silver and pure water combination. This is actually glass and this is mercury. Okay, all right. Let us go to the main point now. The shape of liquid meniscus, how it varies for different liquid. Okay, so let me draw the liquid over here. So we have already understood the example. So this is water and this is glass set, and this, you know, this is mercury. Okay, and this is glass. Okay, this is mercury and this is glass. See, here we will try to understand in terms of mechanics. In terms of mechanics, how this surface is becoming like this. Okay, obviously everywhere there is some forces interplaying. So in this case, we'll have surface tension, adhesive force, cohesive force, etc. Okay, so look, if I take a narrow tube, inside a narrow tube, at the point of contact, suppose this is the point of contact, let us take this point as O. Okay, point of contact O. Here also let us take that point of contact O. Okay, so there are few forces which are acting at the point of contact, and at equilibrium there will be no force acting at this point of contact. Suppose there is a molecule at the point of contact. Okay, so if the molecule is acted upon by equal amount of forces in the up and down or this side, so if there is a perfect balance, then only this point will be staying at this position, otherwise there will be some translation motion, right? So since this point is fixed here or stationary over here, this molecule over here O, then there must be a balance of forces. So at equilibrium, what are the forces, how they are getting balanced by each other? Let us try to understand. So there will be forces, different forces, like the surface tension of the surface tension between the liquid and vapor. See, this is empty, this is air. That means I'm taking that as vapor. This is liquid, as you know. This is liquid, any liquid in general. So this interface is called liquid vapor. So this is solid, this is liquid. So this interface is called liquid solid. Okay, and this is solid and this is vapor. So this is called solid vapor interface. So there will be surface tensions acting between the vapor and solid interface. So this is solid, this is vapor. So let us say this is sigma solid vapor. Okay, at the interface of solid vapor, this surface tension acts like this. And see, this is the force between liquid and vapor interface. Okay, at the interface of liquid and vapor, this is also surface tension. Actually, these are surface tensions. Okay, this is liquid and vapor, which is making an angle theta with the solid inside the liquid, that you can see that. Okay, and there will be a surface tension acting at the interface of this is solid and this is liquid, as you know. So this is sigma SL. Okay, sigma SL. Okay, so these forces we understood, and there is another force which is adhesive force, and that adhesive force will be always acting perpendicular to the solid surface. This is the adhesive force. Let us say this is Fa, adhesive force, which is always acting perpendicular to the solid surface. Okay, or perpendicular to the solid wall of the vessel. Okay, now look, if I break this sigma LV, that is the surface tension at the interface of liquid and vapor, if we just break into component, because this angle is theta, I get two components, two perpendicular components. Okay, this I'm writing here, this is sigma SL. So I have two components of this LV. One is along this way, sigma LV cos of theta, and another one is along this direction. Okay, and see, that is, this is actually sigma LV sine theta. So at equilibrium, this Fa, adhesive force, will be exactly balancing this sigma LV sine theta. And see, this sigma SB, that means this particular force, will be balancing the surface tension of SL plus sigma LV cos of theta. Okay, sigma LV cos of theta. Now this angle of contact, look this, cos of theta, if I just write cos of theta, then what I get, sigma SV minus sigma SL divided by sigma LV. Okay, so now I can understand, I'll be able to get the nature of the curvature at the point of contact from these forces. If suppose, see, let us take first condition, if sigma SB is much greater than sigma SL, then cos theta is positive. Okay, cos theta will be positive. And when it happens, when theta is acute angle, right? Acute angle. When theta is acute angle, that time, or theta is below 90 degree, then what will happen? There will be rise. Okay, SVC, this liquid molecule will be actually pulled up here, pulled in the upward direction. Okay, so that's why the meniscus will be concave meniscus, and the liquid will wet the surface of the solid, so that thing will happen. Now let us take second case, when this sigma SB is less than sigma SL. Okay, that means this one, sigma SL is this one, sigma SL, this one. If this is greater than this one, then the liquid molecule will be actually pulled down. Okay, see, this in this case, cos theta will be negative. Okay, that means, see, it is happening cos theta negative case. That means, you know, the angle is going to be obtuse angle greater than 90 degree, and in this case, since SL is greater than SV, so this, there will be a net force in the downward direction, so the molecule at the point of contact will be pulled down. So that's why the meniscus will be a concave meniscus. At the point of contact, there will be depression. In the other case, it was actually rise of the liquid at the point of contact, but here it will be depression because of this force, like net force of these two. Okay, and when these two are equal, the third case I can write it here. Third case, when sigma SV equal to sigma SL, then cos theta will be 0 degree. That means theta is 90 degree. And that is the case when the plane surface will be the meniscus. Okay, the meniscus will be plane surface. Okay, I hope you have understood according to this distribution of forces or different forces. Okay, now we'll just go to quickly the capillary action. I am already over time. Okay, but I'll take another 15 minutes to make you understand about the capillary actions or capillarity. So what is capillarity? First of all, let me tell you what is capillary. So there is a Latin word capilla. So capillary, the word capillary has come from Latin word capilla, CAPILLA, capilla. This means hair. Okay, hair. And what is capillary tube? A tube which has a very fine bore, just like hair. That is called a capillary tube. Okay, a tube which has very fine bore like a hair is called a capillary tube. And when such capillary tube is dipped into a liquid kept in a container, it is seen that the liquid rises or falls. Okay, liquid rises or falls. Okay, not only rises always, it sometimes falls also. You can see that this is the upper level of the water outside the capillary, and see this one. This, I'm sorry. Uh, Originally, it should be okay. Falling. This is fall. Okay, capillary. This is falling, and this is rising. See the level outside, and here the liquid. So this is the rise. Okay, rise of liquid. Okay, sorry. Let me write here. Okay, rise of liquid. So both kind of action may happen with capillarity. Okay, rise or fall of liquid surface. Okay, so if you take a fine board capillary tube and dip into the liquid which has open surface. Okay, the liquid surface is actually open to the air or atmosphere in both cases. See, this is, see, the liquid surface inside the capillary may rise or fall. This rise and fall of liquid inside the capillary tube is called capillarity. Okay, this property is called capillarity, or phenomenon of rise or fall of a liquid inside a capillary tube when dipped into that, compared to the surroundings. Okay, compared to the surrounding, this is the surrounding. Okay, surface of the liquid, surrounding surface of the liquid, and this is the surface of the liquid inside the tube, capillary tube. So this may rise or fall, both can happen. Okay, both can happen, either rise or fall can happen. Okay, if this figure is not very much representative, let me draw it here. Suppose, okay, this is the liquid. So when you dip, see, this will be like this, this will be like this. The liquid inside the tube will be like this. Okay, see this surface is upper than the surface inside the capillary tube. Okay, this rise and fall both are known as capillary ascent or capillarity. All right, but why does this happen? This is due to this adhesive and cohesive force. Okay, due to this happens due to interplay of the strength of adhesive and cohesive force. Sorry, cohesive force. Okay, between the liquid, okay, liquid and solid surface. Okay, so this is about liquid. Sorry, this is about capillary action. Now we'll just learn the formula for ascent. That means how much height the liquid will rise inside a capillary tube when you dip a capillary tube of given radius, and if the surface tension of the liquid is given, and also if the angle of contact is given, then you have to write the height that will rise inside the capillary tube. So what will be given? Radius of capillary tube, then surface tension of the liquid, surface tension, then what else? You will be given surface tension and angle of contact. So this, you have to find out a formula for the height that rises inside the that the liquid rises inside the capillary. Okay, so we can just derive this formula. How to derive that? Let us consider a very narrow tube of radius small r, and let us take the liquid of surface tension S, and let us take the angle of contact to be theta. Angle of contact to be theta. Okay, now we know, let us just consider this point and this point. We know for a surface, convex or concave surface, always there will be an excess pressure or greater pressure in the concave surface. So greater pressure or excess pressure will be there. Excess pressure, greater is my word. So this is excess pressure. This is called excess pressure compared to this point. If I say this is a point A, this is point B. So at point A, there will be always an excess pressure. So that's why this curved surface is actually maintained. Okay. So there will be always an excess pressure towards the concave surface. Okay. In case of this also, there will be excess pressure in this side, concave side. Okay. So if I consider 2 points A and B, A is towards like in the concave region, and this is just above the meniscus, okay, or the top surface. And let us say this height from the water surface outside is h. So this height is h, let us say. Okay, and see the pressure at B will be then having some amount of pressure less than the excess pressure. Okay, so you know what I'm trying to say. So there will be excess pressure here, but what is excess pressure in case of liquid? Excess pressure in liquid bubble inside, excess pressure. See, this is a part of a liquid bubble over here. If you can see this is a spherical bubble. So this part, this meniscus is actually part of this liquid bubble. Okay, then we can find out what is the excess pressure inside this bubble, right? Excess pressure inside a liquid bubble, and bubbles are liquid bubbles are taken on any bubble here. We take ideally spherical one. If this bore, okay, or the radius of this capillary tube is very narrow, then the liquid bubble will be always spherical in shape. Okay, and what will be the excess pressure? Excess pressure is actually always 2 surface tension theta 2s by r. R is the radius of liquid bubble. Liquid bubble. Okay, radius of liquid bubble. If I know the radius of liquid bubble, then we know the excess pressure inside the bubble. That is 2s by r. 2s is the surface tension. Okay, 2s by r. In case of soap bubble, it will be 4s by r. Okay, there will be two surfaces, two interfaces. Okay, with liquid air. Okay, liquid air. There will be two. All right, because you know in case of soap bubble there will be air here. This is liquid or soap solution, and again air here. So you have two interfaces. In case of liquid, you have liquid here, just here also liquid. Okay, I mean inside there will be no air. This will be just liquid. So you have only effectively one interface. All right, and see for a, so at this position there will be excess pressure. How much? This much. So if I say the pressure is here PA, okay, if I say pressure is here PA, so what will be the pressure at B? So pressure at A, I'm taking just PA. Then pressure at B, at B point will be PA minus this excess pressure. If the total pressure is PA, then it will be PA minus the excess pressure 2s by r. Okay, if the total pressure here is PA, okay, then there will be excess pressure. Oh, sorry, this is the pressure at B. So this is very nice. Now this excess pressure, what this excess pressure will do? So this excess pressure actually elevate this liquid column. Okay, excess pressure actually just drag the liquid up to this height edge. Okay, this excess pressure will actually drag the liquid up to this much height. That means at equilibrium, what will happen? Let me okay, let me just go to this point here, there itself. So I'll just, maybe I'll take this figure over here. Okay, so you can see that this pressure will be exactly equal to the pressure of the liquid column. Okay, the liquid column will give certain pressure at this particular position. Okay, so what is that pressure? So what I am trying to say is that due to this excess pressure, the liquid rises in the capillary tube by height small h. When the hydrostatic pressure exerted by the liquid column becomes equal to the excess pressure P. So at this condition, when there is an excess pressure, that pressure will actually drag the liquid up to this much height. And what we can say about hydrostatic pressure? Hydrostatic pressure H rho G will be exactly equal to the excess pressure over here. Okay, let me clean this portion. Okay, this I know this parameters already. So what I can say, due to this excess pressure, the liquid will be dragged through the tube, narrow capillary tube, up to this height h inside that. So this liquid column inside the tube will also have certain hydrostatic pressure, which will be in the downward direction, that is h rho g say, and this will actually be balanced by this 2s by r, this excess pressure. Okay, now we have got the point. We know there is excess pressure at this point A. That excess pressure will actually drag the liquid up to height this, and when the height will be that much only till when the excess pressure can balance the hydrostatic pressure. Okay, now look from the second figure, this figure B, we have got a relation between, see, if the liquid bubble has got a radius capital R, and this is the radius of the capillary tube small r. So this two has got a relationship. Okay, where this angle is angle of theta. Okay, sorry, angle of contact. This angle of contact theta, if we know, then you look, I get, see, this small r by capital R. Okay, that means this is actually hypotenuse. This is kind of a right angle triangle. This is vertical. This is your base. So base by hypotenuse will be actually cos of theta. Let me write then what is r. Capital R will be actually r by cos of theta. If we put it here, see what we'll get. If we put here, we'll get h rho g is equal to 2s cos of theta by smaller. So you look here, this angle of contact, if it is given for a particular capillary, particular capillary tube, solid and the liquid surface. Okay, if the surface tension is given, if the radius of the capillary tube is given, then see what I get. This h I can calculate as, like, using this formula 2s cos theta by rho small r into z. Okay, so this is actually the formula for ascent or capillary rise. This is formula of ascent or capillary rise. Sorry, capillary rise. Okay, but one point we have not considered here. Look, if we consider, see, if we zoom out the shape of the meniscus, see, we have not considered the liquid which is here. This is actually called liquid inside the meniscus. Okay, liquid inside the meniscus, this we have not considered. inside the meniscus. Okay, liquid inside the meniscus we have not considered. If you consider this liquid, then you know I have liquid column H rho G, this much pressure plus some more liquid will be giving some pressure, extra pressure. Okay, extra pressure. Okay, so that will actually balance 2s cos theta by r. Okay, so what is this pressure, extra pressure here? We can find out actually. How to find out? We have to find out what is the mass of this liquid, and then G, that will be the pressure. Sorry, that is the force actually. Okay, so force divided by area of cross section. Area of cross section of this particular, you have to just multiply so that you get the force if you want to do that. So you know, let me show you how we get actually what we will get modifications. We'll get the modifications in the height as 2s cos of theta by rho rg as we had here minus r by 3. So this much modification will be there in the formula of the ascent if we consider the liquid inside the meniscus. Let us see how we get this factor. Okay, as I said, see if we find out the answer. See, this is it is actually this meniscus is shape of sphere as I showed you here in the earlier slide. Okay, and this is hemisphere. Okay, this is hemisphere. See, to find out the volume of the liquid we get here in the meniscus, what we have to do, we have to take the full volume of this cylinder. Okay, cylindrical part, this cylinder, the whole cylinder, you take this one. Okay, this whole cylinder first. So what is the, see, pi r square, the plane surface into height. Height is actually r only because this is the radius of the hemisphere. This is the whole volume of the cylinder minus the volume of this hemisphere, that is actually 4 by 3 pi r cube into half. So this is actually the volume of the liquid inside the meniscus. Okay, so I'll get here, this 2 will cancel each other, so it will be actually 1/3 pi r cube. Okay, this is the volume, and what will be the mass? Mass will be pi r cube by 3 into rho. And what will be the force due to this? What will be this? And what will be the pressure, extra pressure? That will be divided by the surface area of this capillary tube itself. So I can write pi r square rho g divided by 3. Sorry, this is pi r cube. Excuse me. Pi r square I can write. So this will be actually the pressure, excess pressure, extra pressure. Okay, with h rho g. So this will be extra pressure. Look, this will be actually r rho g by 3. Okay, rho r g by 3. Look, if I just write down here in this expression, let me write down in the p extra. Okay, what is the pressure, extra pressure we are getting due to this liquid inside the meniscus? We have got rho rg by rho rg by 3. Okay, so let me take this h, I have to find out, isn't it? So h rho g, let us take this here 2s cos of theta by r minus r by 3 rho g. Now you just strike out rho g from here and rho g you multiply there. Okay, so 2s cos theta by rho rg or rho gr minus r by 3. So this is how we get the correction factor. Okay, when we consider the extra pressure obtained from this water in the meniscus. Okay, I'll stop it here for today. In the next class, while taking the problem, numerical problem, I'll discuss about what happens while we have insufficient length in case of rise in liquid. Okay, whether liquid will overflow or what happens in this case. Okay, we'll take up this concept in the next class while doing numerical problems on this or conceptual problems, analytical problems from this capillary actions. That we'll do in the tomorrow's class. Okay, so thank you for your patience. Bye for today.